Zip will set things up. And I'm very happy to introduce our next speaker, Dr. Joanne Taylor from Gain Therapeutics. And she'll be speaking about GT-02287, a clinical stage allosteric GCase modulator for the treatment of GBA1-PD. Thank you.
So I'd really like to thank the organisers for this fantastic meeting. It's been a really great few days, and also to thank you for letting me talk about GT-02287, which is our clinical candidate for the treatment of GBA1 Parkinson's disease. So this molecule is an orally available, brain-penetrant, allosteric GCase modulator that was discovered on our supercomputer-based discovery platform. It's a chaperone, molecule which chaperones GCase to the lysosome, and it has neuroprotective and functional effects that we've shown in vitro and in vivo models of Parkinson's disease. And it's currently a clinical candidate in phase 1 in healthy volunteers, which is just about finishing up. And because of all the work that we've done on this molecule, trying to understand exactly how it exerts all the neuroprotective effects in the cell and in animal models, we believe that it has the potential to be a disease modifier in Parkinson's disease and also in other neurodegenerative diseases from other work that we've done. So I don't want to talk today about all the cell-based models that we've done. I want to introduce some of the in vivo work that we've been doing with this molecule, but I just want to summarize here that we've been able in various cell-based models, including patient-derived fibroblasts, patient-derived neurons from induced pluripotent stem cells, and as well as in various models, that we've been able to show that the compound has effects on ER stress, the accumulation of the toxic lipid substrates, as well as alpha-synuclein accumulation. We've been able to show effects on lysosomal dysfunction, also mitochondrial dysfunction, and then in animal models, we've also been able to show effects on neuroinflammation and on motor deficits. So I want to thank Arno earlier for introducing the concept of CBE as a tool, but we've heard quite a lot about that molecule at this conference. So we have used CBE, which is a irreversible GCase inhibitor, to knock down the activity of GCase in wild-type mice to model GBA1 Parkinson's disease. So the effects of doing this in this slide are represented in the red bars. So in this model, when we've treated animals with CBE, wild-type mice, we have seen an increase in the GCase substrate, glucosylceramide. We've seen increases in aggregated alpha-synuclein. We've seen decreases in tyrosine hydroxylase positive neurons, so dopaminergic neurons. Maybe unsurprisingly, we've seen decreases in striatal dopamine in this model because of the, presumably because of the loss of dopaminergic neurons. We've also seen an increase in EBA1 staining, so this is a measure of microgliosis. We've also lost neurons in the cortex. Pretty exciting for us, we've seen increases in plasma levels of neurofilament light chain in this model, so I'm sure you're all aware that this is an emerging biomarker of neurodegeneration. And we've also seen decreases in locomotor ability in the wire hang test, and also increases in lack of coordination in the beam walk test. So in all of these readouts, we've been able to see with various doses of our compound that we can stop these things happening. So the accumulation of substrate, aggregated alpha-synuclein, loss of dopaminergic neurons and dopamine, neuroinflammation, loss of cortical neurons, neurodegeneration, and loss of motor function. So in following on experiments, we wanted to be able to show a therapeutic effect of this molecule. So the experiment I just showed you, we gave CBE and we gave the molecule at the same time. And in this paradigm, we have instigated the model. So in this case, we've given lower doses of CBE, but we've also introduced alpha-synuclein preformed fibrils into the striatum to more closely model Parkinson's disease. And then we have started treating the animals with our compound after we instigated the model. So in this case, either 4 or 8 days post the start of the model. And then we tested the animals in the wire hang test at day 14, so this is about a week after we started treating, or at day 27, which is about 3 weeks after we started treating. And we also measured neurofilament light chain in the plasma at the end of the experiment. So what we saw when we treated gave the animals just a relatively low dose of CBE, you know, there was a little bit of a drop in the latency to fall in the wire hang test. When we treated the animals with alpha-synuclein alone, there was a bit more of a fall, and when a drop in the latency to fall. And when we treated the animals with both CBE and alpha-synuclein together, we had a really profound effect on this motor function. And when we treated in a delayed paradigm the animals with GT-02287, we were able to rescue this effect on motor function. And when we tested after 14 days or a week after we started approximately a week after we started treating, the animals that we started treating 4 days in were a little bit better in the wire hang test than the animals we started treating later. But when we tested them again 2 weeks later, the animals that we had started treating later had recovered somewhat. Obviously, this is a very small increase because we were close to the ceiling already. And again, as we've shown in the previous experiment that I showed you, these deficits in motor function are reflected by increases in plasma neurofilament levels that we can knock down with our compound. So we wanted to go on and look at a bit of a more complex model. So we're looking at a natural behavior of rodents here, which is nest building. And we're again treating the animals with CBE and alpha-synuclein preformed fibrils, and then treating them with our compound, and then looking at the nest building ability. And the nest building is just scored from 1 to 4, basically 5 actually maybe. And anyway, so in the control animals, you give them the tools and they build a really nice nest. We give them the CBE and the preformed fibrils, and it's kind of full-on, teenager's bedroom. It's a mess, and it's all over the place. And then with increasing doses of the compound, the mice are able to build a nice nest again. And this is just quantified here in the nest scoring, and by comparison, we've got the wire hang test. And then again, we have measured neurofilament light chain in the plasma at the end of the experiment, and there's an increase, and we're able to bring it down. Also reducing levels of alpha-synuclein. In this case, we've measured GFAP as well, which is obviously a marker of astrogliosis, and again, EBA1 as a measure of microgliosis. So just to remind you that this molecule is currently in a phase 1 clinical trial. We've completed the single ascending dose part of the trial, and we're about to complete the multiple ascending dose part of the trial, and so far everything looks hunky-dory. So in summary, we have a small molecule, orally available, brain-penetrant, allosteric GCase modulator. It was discovered on our Magellan computational drug discovery platform, or we used that platform to discover it. We optimized the molecule after we found the original molecules. The molecule can reduce ER stress. It prevents proteasomal GCase degradation. I haven't really shown you this here. Increases lysosomal GCase activity, reduces accumulation of substrate and alpha-synuclein, and we also see improvement in lysosomal and mitochondrial function. And as I've just shown you in rodent models of GBA1-PD, we can reduce a lot of biomarkers of ill health, and we can increase striatal dopamine levels. We can reduce motor function and also complex behaviors such as nest building, which, obviously this is a complex behavior, but it does include some cognitive function. We've seen these effects in delayed treatment paradigms, and we've seen this accompanied by changes in neurodegeneration biomarkers such as plasma, neurofilament light chain, and as I've said, we're currently in phase 1. So I'd like to acknowledge my colleagues and collaborators. The in vivo work was carried out by Beatrice Guzman. Jonas Hannestad is our current new Chief Medical Officer. We've also been collaborating with Professor Molinari's group in Bellinzona, and we had a great collaboration with Professor Feldman with the iPSC-derived dopaminergic neurons. And I'd also like to thank our funders and for your attention. Thank you very much.
Thank you. That was fantastic. And now when I go back to New York and my patients say, well, what's new? And I'll say, well, we had this really tremendous conference. All these people came together, collaborations, and there's this new allosteric modulator, and you can build better nests. It's like it's the next level in home porn.
Give it to your children.
Right, yeah. All right. We have a question?
Yeah, thank you for sharing the data set on the CBE. At 100 mg per kg with CBE, is there any GCase left that's unmodified to transport?
Yes, there is. I mean, it is quite a high dose, and then in the subsequent experiments that I showed you, we've given 50 milligrams per kilogram every other day, and then, put the PFFs on top. So people get a little bit confused, with this model, but how we think it works is that there is GCase left. We have measured this, and we think that it's obviously it's a wild type model, so the wild type GCase that also has a tendency to misfold, as all proteins do, that we're getting more of that transported to the lysosome.
As you looked at this, how much GCase is left after 100 mg per kg at 14
Yeah,
days?
it's quite low. It depends on the experiment, but it's maybe 10 or 20% of what we started with.
Okay, thank you.
Yeah.
Thank you so much.
Thank you.
And